All right, welcome to Next Gen Manufacturing. Today we are going to peel back the layers on some of the most advanced products on Earth. We're going to find out what makes them so incredibly strong, but also, surprisingly lightweight. And I'll tell you right now, the secret, it's probably not what you think. So, have you ever really stopped to wonder what's going on inside these incredible machines? I mean, what is the secret sauce that lets a fighter jet pull insane G-forces or a race car stick to the track? What allows them to perform under such extreme conditions? You might think, oh, it's probably just some single supermaterial, right? Some exotic metal or a space-age plastic. But the answer is a little more complex than that. And honestly, it's a lot more interesting. It's not just what they're made of. The real magic, the absolute game changer, is in how multiple materials are combined. It's a partnership, a team effort that's happening at a microscopic level. And that partnership is what gives these products their superpowers. And that brings us to the world of composite materials. I mean, the name kind of says it all, right? They're composed of different parts. But the amazing thing is, the whole is so much greater than the sum of its parts. Let's think of it like a sports team. You've got players with totally different skills. One player is incredibly strong, another is tough and super agile. On their own, they're pretty good, but when they're together, playing their specific roles, they create a championship-winning team. That right there is a composite material. And this slide, it breaks that team down perfectly. On one side, you have the reinforcement. These are the superstars, the stiff fibers like carbon or glass that provide the raw strength. Then, on the other side, you've got the matrix. This is the tough stuff that binds everything together, protects those important fibers, and helps spread out any stress. The easiest way to picture this is rebar inside concrete. One gives it strength, the other gives it structure, and together, they're absolutely formidable. But here's the crucial point. It's not enough to just, mix these two things together in a bucket. No way. The real magic, the key to unlocking their combined power, happens in the tiny, microscopic zone where they actually meet. We call this the interface. Now, the interface isn't just a simple line between two things. It's an active, three-dimensional zone. It is the ultimate handshake between the reinforcement and the matrix. And everything depends on this connection. If that handshake is weak, the whole material fails. But if it's strong, well, that's when you get the incredible performance we see in jets and race cars. So that begs the question, right? If this make-or-break zone is so small it's practically invisible, how on earth do scientists and engineers actually study it, let alone design it to be absolutely perfect? Well, the answer lies in modeling. And we're not talking about physical mock-ups. We're talking about sophisticated mathematical models that let scientists see how forces are going to flow deep inside the material, right down to that critical interface. And the core concept they're all trying to figure out is called load transfer. It's really all about tracing the path of force. So when you push, pull, or bend a composite, that stress has to flow seamlessly from the tougher matrix, across that all-important interface, and into the super strong fibers that are designed to take the brunt of the load. It works in three pretty simple steps. First, some kind of external force hits the material, and it's initially absorbed by the matrix. Second, the interface does its job. It acts like a bridge, passing that force over to the fibers. And finally, the fibers, the backbone of the material, they take on that load and provide all the strength. Over the years, our understanding of this whole process has evolved. Scientists came up with a whole series of models to describe it. The early Cox model assumed a perfect world, a flawless bond, like two things perfectly glued together. Then came the Tyson model, which looked at the opposite extreme. What if there's no real bond at all, and the transfer just happens through friction, like sandpaper? And finally, the Piggott model gave us a more realistic mix, describing a bond that's strong but also has some give, kind of like a tough, flexible adhesive. The Cox model was a fantastic starting point. It taught us that in a perfect bond, the shear stress, that's the force trying to slide the fiber out of the matrix, is highest right at the very ends of the fiber. The only problem is it assumed a level of perfection that, well, it just rarely exists in the real world. So later models like Tyson and Piggott started accounting for the messy reality of the physical world. They introduced things like friction and the ability of the matrix to bend or deform just a little bit. This gave engineers a much, much more accurate picture of what's really happening inside these complex materials. But a strong bond isn't just about mechanics and friction. To truly perfect it, we have to go even deeper. right down to the level of chemistry. This isn't just a physical grip, it's a chemical handshake. This is where we get into something called surface energy. The best way to think about it is as the chemical personality of a material's surface, how eager it is to bond with something else. It's just like how oil and water don't mix, right? Their chemical properties are incompatible. Well, the matrix and the reinforcement fiber need to be chemically compatible to form the strongest possible bond. And this right here, this illustrates the big aha moment. Research has shown there's a thermodynamic sweet spot. When the surface energy of the matrix and the surface energy of the reinforcement fiber are perfectly matched, a ratio of 1:1, that's when you get the maximum possible adhesion, the strongest bond. Any mismatch in either direction and the strength of that bond just drops off. This is where materials science becomes a precision art form. Okay, so let's zoom back out. We've gone from a jet fighter all the way down to a microscopic chemical bond, and now we're back. What does all this mean for the future of manufacturing? That means that this tiny, unseen region, the interface, is the single most important part of the entire puzzle. As the research concludes, it's the strategic zone that truly controls how these advanced materials perform. If you can master the interface, you can master the material. It's that simple. This leaves us with a final thought. We are entering an era where materials aren't just designed by mixing ingredients together. They're designed by engineering the perfect handshake between them, one microscopic bond at a time. This is the future of next-gen manufacturing. So the only question left is, what incredible things are we going to build with it?